Hi everybody, today's video is going to be about acceleration. We're going to take some of the things we've talked about before and look at this as an example. And so what I'd like to do is take some vector valued function r and consider it as the trajectory of a particle. That is that that vector r describes the position of a particle at some time t. And so the derivative of r then, r prime, is just the velocity vector of the particle at any given time t. And the second derivative of r, or the first derivative of v, is just the acceleration of the particle at any given time t. It should be clear from the way we defined the unit tangent vector before that then the velocity vector is just going to be a scalar multiple of that unit tangent vector. But I'd like to make a claim about that acceleration vector, and that is that it's a linear combination of the unit tangent vector and the principal unit normal vector. That is that I can write it as some quantity, perhaps a function of the parameter t times the unit tangent vector, plus some other quantity, again perhaps a function of the parameter little t times the principal unit normal vector. So the picture looks like I've got some curve at some t, at some given t, we're at some point on the curve. We've got a velocity there given by the velocity vector, the derivative of the position. We've got an acceleration at that point, and the idea is that if we look at the unit tangent vector and the principal unit normal vector, that I can express that acceleration in terms of those two vectors as some linear combination. So some linear combination of the unit tangent and some linear combination with the some combination of some component of the principal unit normal. In two dimensions, this result isn't so surprising because t and n being orthogonal to each other, being perpendicular, means that they're linearly independent, and I can express any vector as a linear combination of two linearly independent vectors. So that doesn't seem to be such a big deal. In the space curve example, though, when we think about 3 dimensions, it's maybe not so obvious, because what it says is that the acceleration vector will always lie in the plane determined by t and n. So I'd like to prove this claim, and to start, let's think about what the definition of the unit tangent vector was, and that allows us to then write an equation for the velocity vector in terms of its magnitude and the unit tangent vector. And then if we differentiate both sides with respect to the parameter t, on the right-hand side we'll have to use the product rule, but that's okay. And the left-hand side, the rate of change of the velocity is just the acceleration. So I'll take this result and carry it forward. And what we're going to focus on here is the second term on the right-hand side. What I'll do is just multiply it by 1, so it doesn't change that quantity. But we multiply it by 1 in a clever way so that if we rearrange a little bit, what we notice is that that term to the far right is exactly our definition of the principal unit normal vector. So again, carrying this forward, we see that what we've done are express the acceleration vector in terms of what's called a tangential and normal component. And so that allows us then to write that acceleration vector in terms as a linear combination, just as promised, of t and n. And so that's what we've got on acceleration so far, and sort of being able to tie that into the tangent and normal vectors that we talked about before. You will examine some different ways to express that acceleration vector to find those tangential and normal components in the problem set, and I'll see you guys in class.